Okay, today I will introduce our third-party library version detection tool for Android applications at ATVHunter. Before we start, let's see the background. According to previous studies, third-party libraries are widely used by many apps, but our coin has two sides. Third-party libraries also can bring some security risks, especially the vulnerable third-party libraries, which can accelerate the spread of the vulnerability due to the direct and transitive dependencies. However, identifying third-party libraries, especially at version level, is very challenging. Here we also list some typical challenges here. The first one is code obfuscation. Code obfuscation is often used to protect the software against reverse engineering. It can hide or change the real code logic. Therefore, it can affect the detection performance. Here we also provide some commonly used obfuscation techniques here. Let's see an example. I should emphasize here, our research just focuses on identified Java libraries. We do not consider other libraries. Here is a package tree of a third-party library. Package flattening can remove the whole package hierarchy structure. It's really combined with renaming obfuscation, which can modify the class name, method name, package name, etc., etc. Besides, package name also can modify the internal package structure. It can change the original TPL code feature without a doubt. It adds the difficulties in TPL identification. The second challenge is TPL dependency. Because the time is limited, we won't go into details here. If you have interest in this part, maybe we can discuss offline. The third challenge is various library import mode. There are many modes to import a third-party library, but partial import and customized import can make the imported TPLs different from the original ones. The fourth challenge is complicated package structure. Here we can see some examples here. For the first example, we can see different third-party libraries may share the same root package. But we also can find TPL may also have several parallel root package structure due to the TPL dependency. As we mentioned before, obfuscation can also change the package structure. Package structure among different versions may be mutant. Here we also conclude some module decomplete features of existing techniques. Here we can find most tools, they usually directly use package structure to construct TPL candidate in an app. Homogeneous graph and package dependency, they more or less include some package structure as a supplementary feature. But as we mentioned before, package structure is not stable. Using such a feature can affect our detection accuracy. The fourth challenge is different version similarity. Here, this is because the code gap of different versions of the same TPL are also various. Some gaps can be huge and some of them could be tiny. Here we can see an example. It's two versions of a same TPL, but we only found one operation is different. Therefore, we should carefully choose the feature granularity so that we can distinguish different versions. Here we also conclude the existing feature of current tools. Here we can see further method signature, which means use a placeholder X to replace the developer defined type and variables. Here we can see an example. Two different methods. They may generate the same signature by using fuzzy method signature. I think most of you are familiar with CFG, API, and class dependency. We want to elaborate the details here. As for the CFG centroid, is a three-dimensional vector which can reflect the structure of CFG. But we found all of these features, they have some common disadvantages. The granularity of the code feature are too coarse. Different versions may have the same signature, and the changes of the statements cannot be reflected from the used signature. Besides, fuzzy method signatures and APIs they do not include rich semantic information. They just can reflect the syntax informations. Besides, CFG centroid can be easily changed by the code obfuscation. Therefore, we propose our method ATVHunter. Basically, our method can be divided into two parts. The first one is TPL identification. Second part is offline database construction. As for the offline database construction, is also can be divided into two parts: the TPL feature database construction and the vulnerable TPL database construction. As for the TPL identification, we divide it into 4 steps. The first one is pre-processing. When we get an app, we will compile it and get one or several package trees. Then we need to identify the code from the host app we call the primary module. We need to delete it to remove the interference from the host app and remain the non-primary modules. Then we will conduct a module decoupling algorithm. Based on our analysis, we know that the package structure is not stable, but fortunately, we found class dependency graph can achieve a good performance in construct TPL candidate instance. Then we need to extract the code feature from the TPL candidates. If we want to achieve a good resilience to code obfuscation, we need to include the feature with the rich semantic information. Therefore, we choose CFG as our feature. In order to distinguish different version similarity, we need to include some fine-grained features. Therefore, we choose opcode as our version feature. In order to effectively handle various import mode and code obfuscation, then we use fuzzy hashing to generate our features. Here we can see the handling process. We generate a CFG for each method and we change it into adjacency list. Then we calculate a hash value for each CFG. Then we sort these hash values in a class in ascending order and connect them as one string. We calculate these hash values to generate the class features. Then we use the same method to generate to handle the class features to generate the TPL feature. For the fine-grained feature, we get opcode sequence from each CFG adjacency list. Then we use a rolling hash and slide window to generate the version fingerprint. For the last step, we adopt flexible comparison strategy to handle it. Firstly, we will check the packaging name of TPL candidate is obfuscated or not. If not, we will use a packaging name to narrow the search scope. Then we will compare the TPL feature. If we find the match pairs, we will stop our searching process. Otherwise, we will use class features to find the potential TPS. If more than 30% of the class feature are matched, we consider find the potential TPS. Then we will compare the version feature to determine the used TPS. For the evaluation part, we use 3 metrics to evaluate ATVHunter and the state-of-the-art TPL detection tool. Because the time is limited, we won't go into the details. We find that ATVHunter can achieve a good performance at library level and version level. ATVHunter is also more efficient than other tools. Besides, we also conduct a large-scale analysis for the apps from the Google Play to identify some apps include the vulnerable third-party libraries. We want to elaborate the details here. If you have interest in this part, you can visit our website and or refer to our paper. If you want to use our tool, maybe you can go to the second link. This is all on my presentation. Thank you for your listening. Thank you.
Hi. Welcome to the last to the last paper of this session.
Okay.
So Xian is here with me,
Yeah.
and she's one of the authors of this extremely good paper, ATVHunter, reliable version detection of third-party libraries for vulnerability identification in Android applications. So I'm Alessandra, and I'm happy to pose any question to Xian. So please post on the chat all your questions. And I do want to congratulate again Xian for the award for this paper.
Thank you.
And especially, I would like to congratulate you because this seems to be quite an explored topic. So there are already so many papers on library identification for Android apps that I mean, it is really impressive that you managed not only to have a contribution, but also such a strong one to even get an award. So congratulations twice.
Thank you. Thank you.
So while we wait for questions from the audience,
Okay.
um, I was wondering. So yeah, I see people clapping. They can do it.
Thank you. I
Um,
really
so
appreciate the word because before this paper was accepted, we have rejected twice.
that's normal. That's the normal life
Yeah.
of researcher. But it's good to mention this, especially to people who experience multiple rejects,
Yeah.
because it
Yeah.
is good to know that even paper that get awards get rejected before. It's totally normal.
Yeah.
So, question. I was wondering. Maybe you have it in the paper, but so somehow I missed it. If you deal with somehow with the problem of code elimination, because sometimes when an application includes a library, sometimes some part of the library gets removed
Yes.
to save space. So I'm not sure if you deal with this problem, and if so, how you deal with this.
In fact, this is really challenging because except the code elimination, sometimes the developers they usually choose partial importer mode to import third-party library. If the code they just import a few part of code, maybe we will miss this code. In fact, we have conducted this experiment. We found we only can identify about 30% of this code if they have with code elimination. We also cannot solve this situation very well, but we still have some ideas to handle. We will still work these challenges, and we'll also find some method to solve this uh, situation. Maybe you can follow our future work.
Okay, okay. Well, good luck with that, because I know
Yes.
it's a challenging problem. So there is a question from the audience. So Konstantin is asking, how did you choose the 70%
Oh,
threshold?
that is a good question. The shareholder will choose based on many clone code detection. Well, based on previous experience, we found that choosing 30% can achieve a good performance, and we'll also conduct some experiment. We found that choose 30% can have a good performance.
Okay,
Most study were based on previous clone detection method.
okay. Did you also try other values just
Yes,
to?
we try a lot of values, but for some extremely cases, such as the elimination third-party libraries or partial import, maybe we only can find 20% is good. But because we collect more than 3 million third-party libraries, we found by using this threshold, we can achieve a good performance.
Okay. I was also wondering how your technique is resilient to the use of multiple languages. So I wonder if well, I guess it's not a problem if there is Kotlin, because in the end it's compiled to bytecode, but maybe it's not. So please comment on that. And
that's a good question. That's a good question. Actually, Kotlin can be decomposed into bytecode. It's the same with Java library. So Kotlin library cannot. Our method can handle Kotlin libraries. We have found a lot of third-party libraries of Android. They're also developed by Kotlin. But we found because they also can compare it into bytecode, so we can handle it very well.
Okay.
But we cannot handle native libraries.
Okay, that was my next question about native library. Yeah, so native is still a challenge. Okay. And then I was wondering, so regarding the ground truth
Okay.
that you computed, so you did it on some open source applications, obviously.
Yeah.
But then I would like to understand how exactly you did it. So you manually looked into the code just to be sure
Okay,
of
I see.
libraries.
Actually, why we use open source app, because we can find the dependency third-party libraries from the config files. They have developers have already write the dependency third-party libraries into the config files. Usually they write into the ground these files. We just only pass these files, and we can find which third-party libraries used by the host app.
And I was wondering if you still had to manually analyze the code to be sure.
Yes.
Because maybe sometimes the version of the library is not specified, or maybe I don't know. Some weird cases.
Yeah. We found some we found some cases. They just give the artifact ID and the group ID. They didn't show the versions. We will delete. We will remove these apps from our dataset, so that we just keep the version. We can guarantee it.
And another question is about like qualitative analysis. So if you did check which third-party libraries could not be correctly identified, and why, what are the reasons behind this?
The situation is very complicated. For example, we cannot identify third-party libraries. Maybe they also depend on other third-party libraries for these situations. If they only change the field code and most of the core code from other third-party libraries, maybe we will meet the false negatives. And it's really good questions. And for some third-party libraries, we can find the minor version third-party libraries. They only changed one code, one statement. They are very similar. If the code feature sometimes cannot distinguish